Good morning, everybody, and welcome to this new lecture in the series Big Data for Engineers. Today, we will finish what we started last week, which are distributed file systems. The main difference, as you might remember, is that when you look at S3 or Azure Blob Storage, these are services, right, on the cloud that the cloud providers provide, and you just go ahead and use them, right? It's off the shelf. HDFS and distributed file systems, in this sense, are a bit different because these are systems that you have to install yourself on your own nodes. So as some people asked, I can also tell you that there are two ways that you can use them. The first one is by buying your own servers and installing it manually. But of course, then that works if you're a large company, you can pay people to maintain the cluster and so on, do the updates of the system and so on, and support the users. But there is also another way, because it turns out that Google Cloud, Amazon, Azure, they all have special services that you can also use to set up a cluster of HDFS just by the click of a few buttons. It's called HD Insight in the case of Azure. It's called EMR for Elastic MapReduce in the case of Amazon, and Google Cloud likely has something similar. So you see, you have the choice. But even if you use the cloud, the machines are yours, not other people's. So it's not like S3 that is a global worldwide service, you know, where your IDs are unique with the entire world. In HDFS, it's your own virtual machines that are just for you and whoever you authorize, right? So this is the main difference. All right, so this is the high level, right? And of course, both are good to storing data. You can use these cloud services that we saw in series 3 and series 4. You can also use that in order to store your data sets. All right, let me ask you a question on HDFS to check that you have been following. And here you go. What is not stored on the name node? Is it a mapping from files, the path actually to the files, to lists of block IDs, or is it the file namespace? Or are these replicas of the blocks that are 128 megabytes each? Or is it a mapping from block IDs to lists of data nodes? So 3 of these are actually stored on the name node, and 1 of them is not. So let's see your answers. And there is a vast agreement, which is because it's the replicas of the blocks. Why do we not store the replicas of the blocks on the name node? Anybody?
Yes. Yes, so the student said because the data are stored on the data nodes.
Yeah, exactly. That's why. It would basically be too big, right, to store on the, oh, surprising. That's downsized. All right. So this is indeed correct. The replicas of the nodes are on the data nodes. There are so many of them that this is the part that we need to actually distribute over the cluster. But all the things that I've shown you, the other 3, they are all indeed on the name node. So remember, that's the logical model. I think it's difficult to be simpler. We can be even simpler with object storage, right? Then you just have a key value model. But in HDFS, you have your file namespace. So that's the hierarchy of directories and files. And every file is made of blocks, right? That's the logical level. And physically, so pay attention, this is logical, this is physical. Physically, you take the file, you divide it into these chunks that we call blocks, you replicate them, and you store replicas on the name nodes in. And I also shown you last time, these are the 3 answers that were incorrect in the sense that they were actually stored on the name node. The file namespace is on the name nodes. The mappings from the path to the files to the block IDs are also on the name node. And the mappings from the block IDs to the data nodes, so basically to the IP addresses, for example, of the data nodes, they are also on the name node. what's important to realize is that with this, you can reconstruct all the files. If somebody asks to see a file, you have everything you need, right? You see in the file namespace if it exists, then you locate the you find the block IDs that the file is made of, you look where they are, and that's it. And of course, I will explain to you the whole communication, how that happens. But what's important is that you realize that this is all you need in order to reconstruct that logical model. All right, and again, this is the physical implementation. That's what the users do not see, but I'm telling you that's the secret of how it's actually implemented. All right, so this is the architecture with the name node and the data nodes right there. I also wanted to say a few things on the data node, even though by now you probably know that what is in there, it's the blocks, a lot of them, because you can just do the division, right? Each block is 128 megabytes. Let's assume the hard drive has, let's say, 10 terabytes, and you can do the division, right? Let's do it together. I'm very bad at these divisions with prefixes, but so that's 1/8 of a gigabyte, right? 128 megabytes. 8 of them give you a gigabyte, and you have 1,000 gigabytes in a terabyte. So there's 8,000 blocks in a terabyte. And if your hard drive has, let's say, 10 terabytes, then you can fit 80,000 blocks. So you see, this is why there's a lot of them. You can fit up to 80,000 of these, and maybe even more if you have a larger hard drive on each data node. And somebody even did the division. Yeah, so thank you very much. Absolutely. And indeed, the reason you're actually more correct than I am is that I said terabytes and not tebibytes. When I did the actual 8 times blah, 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 that was kind of a mixture of that. I used 8 with the powers of 2 and 10 to the powers, with the powers of 10 from giga to tera. Why am I doing that? Just because I'm approximating. So this is why I don't care. I'm just approximating things. That's the sort of things you can also do in a job interview if you ask. But thank you for providing the exact answer. All right, so this is what there is on a data node. It's actually boring, and you can actually try, if you manage to connect to one of the data nodes in the cluster, if you create one, try to go inside and look at the file system. These are actually local files on the hard drive of the data node. Each block is actually a file. But of course, this is only visible from the user. All right, so it's a local disk. And because of that, every data node can immediately see if there is a failure of the disk or a block that is corrupt or anything. You can immediately detect that and then report that to the name node, right? That's the locality. As I said, block IDs are actually 64-bit integers. Just think of them as large integer numbers. That's all really what it is. And you see there are so many of them that you don't have any collisions. They are all unique. And given one of these block IDs like this, you uniquely identify the block. And you can even, if you want, access only parts of a block and not the entire block. So you say, okay, here's the block ID I want, but please only give me this if somebody outside the data node asks for that. Then, of course, you might be objecting and thinking, but you told us it's not random access. So why would anybody want to access something smaller than a block? We'll see in the MapReduce week why that is actually useful and why that doesn't actually mean random access. All right, but I'll come back to that. It's just a small cliffhanger to a future episode. All right, so now let's look at how all these nodes communicate together, right? So this is the client, that's whoever is using the HDFS cluster, you, for example. This is the name node, and here I put 2 data nodes, right? Of course, there can be 1,000 of them, but I just put 2. And we look at this protocol. So there's a protocol to communicate, with each other. So let's start with the client protocol, this one here. So what happens is the clients, you, can connect to the name node, and you can say, for example, please create that directory, please delete that directory, please delete that file, please create a new file, right? And so this is the sort of things you do. And if you want to create a new file, for example, I have an animation for that, but the name node is going to say, okay, I created that new file, but now you need to upload the blocks, right? And then it transmits the data node locations to which the blocks of the new file should be updated, right? I'd have an animation for that. And the block IDs are, if you want to read a file, then you request to read a file, and the name node is going to tell you, fine, you go ahead and read that file. These are the block IDs, right? And these are this is where they are located. But then it's up to the clients to actually get the blocks, as we will see. So they get from the name node the block IDs and the data node locations. And we saw this is what there is on the name node, right? It's all on the name. Okay. Second, so this was first, this was this one. Let's now go to this one, the data node protocol. So what happens between the name node and the data nodes? What happens is first, when a new data node joins the network, because yes, that's dynamic. It's like the blockchain actually for mining Bitcoin. It's the data node can leave and join, right, at will. That makes it just easier to manage your system because computers can crash. You can add new machines. You can also double the number of machines if you don't have enough space. So this is dynamic. So you can register to the name node as a new data node. It's basically just, hello, I'm here and I'm a new data node, and you can send blocks to. It's basically what it means to register. A heartbeat is something that happens every 3 seconds. You can change it, of course, but by default, it's 3 seconds. So basically, it's the data nodes every 3 seconds connecting to the name node saying, hey, I'm still here. Hey, I'm still here. Hey, I'm still here. And it just does it all the time. Of course, it's a computer, so it's not boring for a computer, right? But basically, every 3 seconds, it's just going to confirm that it's still there. Why? Because that way, if the name node no longer receives a heartbeat, then it knows that something's wrong with the data node. And at some point, it can just declare it as lost, right? So this is the reason. It's just a sign of life. Then you can also send block reports. That's basically the entire list of all the blocks you have, with some hashes, which is a cryptographic way of checking their integrity. This happens every 6 hours. That's also configurable. It used to be 1 day, now it's 6 hours. This is something you can change. But basically, every couple of hours, you send a full list of all the blocks you have, and that way the name node just has the overview, right? It maintains the overview of everything. Not the actual blocks. This is too much data, just the block IDs. And finally, there's also a way to acknowledge that you received the block from a client when a file is created. So once you have received the block, you can just tell the name node, hey, I just received that block, and that's it, right? What's important is that it's always, always, always the data node that connects to the name node, right? Always. It's never the name node that connects to the data node, never. So what happens is that when the name node wants to give instructions to a data node, it just waits for how much time? 3 seconds for the next heartbeat. And then the next heartbeat is going to use that heartbeat to answer back as part of the heartbeat. By the way, please, for example, replicate that block. There's only 2 of them. We need 3. Please make a copy of it on your machine. That's an example of instruction that the name node can give to a data node, right? Or maybe it can give the instruction, okay, we have too many of these replicas for that block. Please delete one. Right, that's another instruction that the name node can give to the data node. You see, it's low level. This is just how they communicate with each other. All right, and the third one, that's this one, this part right there. No, actually, this entire part, all of that in a single slide. So I showed you this, I showed you that, and now I'm showing you this. What happens is that once the client has created a new file, it's supposed to upload the blocks to the data nodes. And what happens is that it's connected to the first data node because it has to be replicated 3 times every block. So it connects to the first data node and not to the others. Why? Because it's simpler. What actually happens is that it will ship the block to the first, and it will instruct the first to also pipeline it through to other data nodes. So there is actually a pipeline that is opening, a communication pipeline, and the data node here directly communicate with each other in order to replicate the blocks. So all the replication of the blocks is done between the data nodes, right? So it's actual data. You can imagine the vast quantity of data that is flowing between the data nodes, but this is for the replication pipeline when you write files, all right? So this is how it works. This is the overview. So basically you can see that the data only ever flows, here I list it's data here and also data here. So the data flows between data nodes and the clients, and all the rest is only control. This is only meta communication in order to do some administration stuff, all right? The data, the blocks actually flow right there. All right, and that's the name. This is the client protocol, this is the data node protocol, and this is the data transfer protocol. If you're interested in the fancy names that were given to these protocols. A protocol is just a language, right? It's just like we're speaking English right now. These speak a protocol with each other. And of course, they must agree on the protocol because otherwise they don't understand each other. All right. So metadata, as I said, is creating a directory, deleting a directory, writing a file, appending to a file. I told you it's possible as well for logging, reading a file, deleting a file. This is all what you can do talking to the name node. So now comes my animation. So I hope I did a good job animating all of that, but then you will understand what's going on. First, I'll start with reading a file, then we'll look at writing a file. So let's read a file. With whom does the client right there initiate the communication?
Yes. The name node.
Yeah, exactly. This over there. Yeah. So the client connects and asks for the file that it wants to read. The name node has all the metadata. It has the file namespace, it has the block IDs, it has the locations and so on. So it's going to reply to the client saying, okay, fine, you want to read that file. First, it exists, good news. Second, these are the block IDs that you need. These are the locations, the block locations that you need to read them from. And it even gives you multiple data nodes to read them from, sorted by distance. You see how nice the name node is with you, right? It's going to sort them the nearest first. Why? Because communication is not instantaneous over the network. You know, especially if you play video games, that the closer you are to the server, the faster it's going to be, the less latency you're going to have. So this is why it's going to give the data nodes for each block ID sorted by distance, increasing distance. Yeah. All right. Then what happens is that the client is going to just go ahead and start reading the blocks, streaming through from the data nodes. So let me explain what's happening right there, because there's this thing I need to explain what's going on right here. So technically, what's supposed to happen on a low level is that you're supposed to take the block IDs one by one, and for each block ID, connect to one of the data nodes and download that block, 128 megabytes. Then you go to the next block and the next block and the next block, and then you basically downloaded everything. That's for a sequential download, if you want to actually download the entire file. If there's not too many blocks, that's actually possible. Now, it turns out that the developers of HDFS made it actually convenient for somebody who just wants to do that. So they don't have to actually themselves fetch the blocks one by one. So it turns out that there's a nice Java library that does it for you. So basically, if you know Java, you know it's called input streams. So you basically just create that class with the actual file that you want to read. And this Java class is going to take care of actually fetching the blocks from the data nodes for you. And the actual programmer in there doesn't even see that there are blocks that are being read. So it's just a convenience of the Java library. But again, that's already low level, because that already assumes that somebody is actually writing a Java program, right? And again, some people might prefer Python, and there's also other ways of reading HDFS, right? All right, but basically what's going on here is that the client is reading the file, and there's this nice library in Java that is fetching the blocks one by one. All right, so that's reading a file. That's the easy part, actually. But now let's go write a file. With whom does the client initiate the connection?
There is a question in the chat.
Oh yeah, let me take the, yeah, go ahead.
If a file is divided into many blocks, shouldn't the block hierarchy matter first, and not how close the data node is to the client?
So here, the first thing I need to say is there is a hierarchy of files, right? In the name node. There's directories and files. The blocks are not a hierarchy, right? A file is a list of blocks, just a sequence of blocks, but there is absolutely no hierarchy. Hierarchy assumes that there is some kind of tree structure, like a genealogical tree, for example, parents, grandparents, and so on. But the blocks don't have any such structure, right? It's really a flat list of blocks. Even the way they are stored, it's all, of course, it's all mixed between all the files. They come from plenty of files, but it's flat. It's just a flat list of blocks. That's all, right? So there is no hierarchy. What you might have meant, because I saw another comment on the chat, is do you parallelize in any way? I'm not sure if this was also what was meant with the other question. Yes, the blocks have an order. I see that absolutely, they do have an order. It's a sequence, it's a list. So there is an order, but it's not a hierarchy, right? A hierarchy assumes that there is some sort of higher structure. It's really just a list of blocks. Now, what I showed you here is a specific scenario. It's a scenario in which somebody wants to read a file sequentially, block after block. This is one possible way of using HDFS. You can do that. There is, of course, another way, which is to read in parallel. Instead of having just this machine right there, you might have 10 machines that in parallel read blocks. And this is something we'll see with MapReduce when we'll actually start doing that, right? But here it was just a simple example where I read them sequentially one by one without actually parallelizing yet. I'm coming to it later. All right. Did I answer your questions, or is there anything remaining that I need to answer? So you meant the order with the hierarchy, right? So, okay, all right, so I got that right.
So if blocks have an order, you can stream the file. If it's sorted by distance, we need to wait to receive everything before sending it.
So there are several things to consider here. There is the fact that let's consider one single block. A single block, the reason why you have several locations is that maybe one will fail. Maybe you connect to the first one and then it doesn't work. The node doesn't work. Then you go to the second one. You just try out the closest to you that actually works. This is for one block. Now for several blocks, in that example we are reading sequentially, you could actually, you know that on your computer, you can run several programs simultaneously, right? So you could also read actually from different data nodes at the same time. So maybe you want to fetch actually the first 3 blocks at the same time, right? So maybe you can connect to 3 data nodes simultaneously and at the same time, download these 3 blocks, right? This is all handled automatically in there. Maybe it's actually doing that. It might absolutely be that this library actually parallelizes a bit the download. But what I'm saying is there's no parallelization on the number of machines that there's only one machine in that specific example. All right? Did I answer? Is that clear, or did I make it worse with my explanation? So specifically on your question, you do not have to wait to receive everything. It's also fine if you already go ahead and start downloading the next one without having fully received the former one. What's important is that you reassemble everything correctly on your side. Okay. All right. It's actually a bit like when you watch a video on Netflix. You know what happens, right? It's streaming on your screen the actual series, hopefully frame by frame in the right order if you want to actually understand what's going on in the series. But in the background, your computer actually already downloaded a few more minutes of your series. It's called buffering, right? And that can actually also happen. You're reading bit by bit the data, but maybe the library is already buffering and is a few blocks ahead in terms of download. Right. Yeah, and yes, you're correct. 1 terabyte will take a long time to download. In fact, that's exactly why we'll have parallelism later, right? That's the whole idea of inventing that. All right. Even though nowadays with the optic fiber, 1 terabyte is actually manageable, right? But again, we'll come back to parallelism with MapReduce and Spark. I'll have plenty of more weeks to actually talk to you about parallelism, to read the blocks in parallel. That's the whole reason for IGFS. All right. So let's write now. So if we write, it's the same. We communicate with the name node and we say, okay, I want to create a file. And then the name node answers and says, okay, fine, let's create a file. Here are where you should put your first block. You need to start with the first block, right? So these are the 3 data nodes, for example, that you should upload your first block to. So now the client is connected, as I explained earlier, to just one data node, but it asks that data node to organize a pipeline with the other 2. So the data is actually flowing like this, right? And then what's going to happen is that the data is sent over. And this is actually sent over using some low-level network protocols. I'm not going to go into the details of these network protocols because it's actually optimized and there is a little bit of parallelism there, but this is purely network. So again, you're not computer scientists, I'm not going in there. But the idea is that the block is sent, right? So the 128 megabytes of the block are sent in there and pipelined through. And then at some point, there is an acknowledgement received that says, okay, we've received your block. So that's it, we received your block. And then the client just goes on and asks for the data nodes for the second block. And then you go ahead, the same, organize the pipeline, receive the acknowledgement, send data over, receive the acknowledgement, third block, and so on. Then it just iterates block after block. So in that case, you really need to go block after block. This is because you're actually writing a file and you need to produce the blocks one by one. Okay, any questions on that so far? So that's the animation. All right.
So there is one. Are are the 3 data nodes used to create the 3 copies?
Yeah, that's exactly what they are here for. Yeah, there will be a copy here, and a copy here. But it's just pipelining in order to optimize. It's like, you know, in some series, in villages, when you want to propagate information, you have this phone tree that you give the information to one inhabitant of the village, and then they call 3 people, and each one of these people calls 3 more people, and so on. That was before the internet. This is how you propagate information. It's just more efficient. So this is why you have this pipeline in there instead of communicating directly with the 3. All right.
So another question is the client just trusted? If they claim to the data node, store it there, do they just listen?
Yeah, you have that. That's another aspect. That's not the blockchain there. Unfortunately, I'm not giving a super cool blockchain and Bitcoin lecture, right? So we are not solving the security problem that anybody worldwide can actually connect and it's secure. That's not the case here. Here we are assuming that all these nodes are nodes that you control. These are controlled by your system administrators. This is one of your employees connecting. So you assume they are all authenticated and they are authorized, and you trust them. Right, any other questions? All right. And if you're interested in the blockchain, and actually it's called the Byzantine generals problem, actually, this computer science problem that was solved with the blockchain. And there are lectures. I think it's Roger Wattenhofer who gives this lecture in ETH about distributed systems. So if this is something that interests you, you can visit the lecture. All right, so, and then of course we finish and release the log. All right, and then there is some more paperwork going in there that you check that the replication is enough, and so on and so on and so on. That's part of the data node protocol. I'm not going in detail. It's just basically checking that there are enough replicas out there in case something happens. All right, and then there's the final acknowledgement that basically says, okay, fine, the file is created, and now everybody can read it if they want. Right. And then, if needed, there will be, but later on, some more replication. If one of the nodes crashes, then you replicate and so on and so on. Something I haven't said is that these 3 nodes right there are never the same ones. For every block, it's going to be 3 other nodes, right? There's diversity in there. All right. Okay, but let me say something about these 3, how they are picked. Because the number of replicas per file, by default, is 3. Each block is replicated 3 times. You can change that number 3. For example, you can make it 5. But whenever you change it, that's for an entire file. Right? So you can say for this file right there, I want 5 replicas of each block. Okay. So now, how do we place the replicas? Well, it has to do, as I said, with network cables and bandwidth and so on and so on. So you basically want to be reliable. You want to also take into account that the bandwidth is limited on the network cables. And you want to have some distribution of the blocks over your cluster. So the idea is that you need to come back to the physical layout of the data center. As you know, there are these rooms filled with these towers that are called racks, and each rack is made of plenty of nodes. They are just piled up on top of each other, right? Tack, 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 tack. Maybe 10 or 20 of them give you a tower. So of course, if you communicate within the same tower from this node to this node, it's going to be faster than if you communicate between this node right here and that node right there, right? Because there is more network cables to basically cross if you want to access. So this is why we need the notion of distance. And the idea is that 2 nodes in the same rack, in the same tower, in that case, we'll have a distance of 2, 1, 2 on that illustration. And in that case, if you take 1 node here and 1 node there, it's 1, 2, 3, 4. So we have a distance measure, right, that tells us how far away 2 nodes are. So this is very close because they're on the same rack. This is further away because they are on different racks. And then you can even add the notion of room, the notion of data center if you want, so to have larger distances. Now, here's how it works. When you select, you want to write a new block, the first replica is going to be stored on the same machine as the client. The same machine as the client, right? So let's call the rack A, where the client is. The second replica is going to be stored in a different rack, a different tower. That's to have a bit of diversity, right? Because the rack might crash, and you want to be sure that it's also replicated to a different rack. So the second replica goes in a different rack, and the third replica goes in the other rack B, the same second rack, but a different node, right? So rack A, and then rack B and rack B. But of course, B is going to be different for every block. And then if there are more replicas than 3, then the idea is that you try to have at most 1 per node, because it's totally useless to store it twice on the same machine, and at most 2 replicas per rack, because having more than 2 for the same rack basically creates, I think it's called in German, a Klumpenrisiko. So you have everything at the same location. I'm surprised that nobody asked a question here, because something must have disturbed you in what I just said. Nothing disturbed you? Yes, that's exactly what should have disturbed you. So Wenshi,
yes.
what is it that disturbed you?
I'm sorry. I'm sorry, Gisela? Can you?
Oh, on the Zoom chat, somebody got exactly what I wanted you to be disturbed about.
Oh, yeah. So the question is client is in a rack?
Yeah, that's exactly what should have disturbed you, because I didn't say that the client was a rack. Maybe you thought, okay, the client is your laptop, right? And your laptop is not in a data center. You would know that, right? If your laptop were in a data center. And I just said, okay, the same node as the client, which is in rack A. So I implicitly say, okay, the client is in a rack. And here you will immediately understand, when we actually start doing MapReduce, the clients that you connect to, that you use in order to use HDFS, is in general going to be one of the nodes in the data center. All right. There are 2 reasons for that. Let me give you the 2 reasons, the 2 cases where your client is actually a node in the data center. The first case is that when you create a new cluster of machines on Amazon or on Google Cloud, on Azure Blob Storage, clicking a few buttons, and then suddenly you have 10 machines in the cloud for you with HDFS. What you're going to do is connect to one of the machines and then do everything from that machine. Typically, it's on a command line. You know that's the terminal window in which you type commands. That some of you probably, maybe a lot of you used it before. If you didn't, then it's an opportunity to actually get used to it. For example, with the git clone, git pull that you did to retrieve the exercises, that's what you do on a terminal. So what happens is that the first thing you do is you connect to one of the nodes in the data center. There's a software called SSH. SSH is a way to connect remotely to a machine on a data center. And then you can start typing things on your laptop, but it's actually executed on the data center. This is what SSH is doing. So what that means is that the client that you're using to connect to HDFS is actually the machine that you're connected to in the data center, and that machine is on a rack. It is actually one of the data nodes, typically, or maybe the name node, right? Okay.
So there are other questions.
Yeah.
So first, what if there is only one client? One node will store everything. The second question is that is there a higher probability that if one node fails in a rack, that the others also fail?
So let's start with the first question. Indeed, if you have only one client, then you would have all the replicas on the same machine, right? So of course, if you keep using the same machine and so on, it doesn't scale. But this brings me to the second use case that I wanted to give you of why the client is actually in the rack. And the second use case is actually MapReduce and Spark. Because the client, it's actually going to be clients, and the clients are going to be all the data nodes. Because each data node, we will see in the future, also runs Spark and MapReduce and this compute stuff that you're basically querying your data with. And as a consequence, every single one of the worker nodes is a client. And now you see there's not only one client, there are actually 1,000 clients because they are all running on the data nodes when you actually use MapReduce and Spark. But I haven't taught you MapReduce and Spark, right? So I'm keeping it for later. So that's just an appetizer to tell you that in the future, we'll actually have all the machines, they will all be clients, basically. And then it makes sense if they all write in parallel, then the blocks will be nicely distributed all over the cluster. All right, does that answer question 1? Let's assume so. Yeah, wonderful. So let me go to question 2, and the answer is yes. There is a higher probability that if a node fails, then a node on the same rack will fail too. It's just the way they are connected, right? Imagine that the reason for the failure is that there's an electric switch that basically just goes down for the entire rack. Then the entire rack is down. So this is why we try to diversify also the racks, because the probability that 2 racks are going to be down at the same time is smaller, right? So that's the reason we try to replicate. All right. And the idea is that that's the clients. These are the other replicas. And if you have 2 blocks now, then the first replicas of the 2 blocks are going to be here. But for the first block, the other 2 replicas are here. For the second block, the other 2 replicas are there. Now you might have wondered, why don't we store the second replica also on the same rack? Hey, but then you see that there's a Klumpenrisiko. Everything is basically now at the same place. So this is why we don't do it that way, but instead we do it that way. Right? First replica on that node, and then you go for the other 2 replicas to a different rack. All right. Okay. So let's move on. Don't hesitate to ask more questions if you have more questions. All right. Now, there's a problem with that system. Do we have a question?
Yes. Why are the other 2 on the same rack and now not on a third rack?
That's for the replication pipeline to be more efficient. I guess that would be my best guess, because you have a pipeline of the data flowing through, and it's more efficient to flow the data between 2 nodes on the same rack than yet a third rack. It's basically non-optimal. So it's a compromise basically between the bandwidth that you have and the failure risk, right? Of course, if you don't like it, you can change it, right? That's just the default behavior of the way it's written.
Yeah. Another question is that if we have many clients, do we connect to many clients via SSH at the same time? Or is there some additional protocols used for this?
There is an additional protocol. This will be all handled automatically by MapReduce and Spark. You won't have to connect to SSH to all these nodes yourself. This is really something that's going to happen automatically as part of MapReduce and Spark. But again, we'll come back to that when we actually study MapReduce and Spark. Right? It will all make sense and add up. Okay. Okay. Now, there's a problem with HDFS. Is that if something goes wrong with the name node, then that's over. Because if you lose what is in there, you can no longer recover the files. Because this is where you know how the blocks assemble to files. Here, you only have the blocks themselves. If I only give you that, then you have no idea what the file hierarchy was, and you have no ideas what blocks belong to which file. This is a single point of failure, and this is really, 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 really bad in a network architecture. So what do we do? Remember that this is what we stored on the name node. These 3 things: file namespace, mappings to the block IDs, and to the block locations. Now, what we do is that we actually do backups, just like backups of your laptop, right? We back that up, So the file namespace and the block IDs, we write them to persistent storage. It's basically some hard drive attached to the network or something. And you just save it to what is called the namespace file. And then, so this is a snapshot, basically do the backup. And then as people add files, you don't actually modify this every time, you just have a log. You basically keep a journal of all the changes that you make, and that just every time you add something, and of course it grows bigger and bigger and bigger. Why do we not persist, however, the mappings to the block, to the data nodes? This is something we don't do backups of, right? Nobody? Let me tell you then, it's because we don't care if we lose that, because when the data nodes connect to the name node with the reports, we will actually recover all of that. You just need to wait until the next reports or request a report from the data node, and they will tell you themselves what blocks they have. So this is why we don't need to back that up, right? Hope that makes sense. But this we need, because otherwise we lose data. All right, and of course this grows bigger with time. And at some point we have the problem that it's too big. Also an extra precaution, we back up this, we back that up to some drive, and we additionally do even more backups because we are paranoid, it's company data and so on, we don't want to lose it. So there's plenty more backups on tape, for example, in bunkers and so on, so you can further do backups of the backup. Right. All right. But here's the problem. If it fails, we have the backup. So first, not everything is lost because we have the backup. The problem is that we will still need time to restart because we need to now restore the backup. So this is going to take actually half an hour. Why? Because we need to first reconstruct from the namespace file the first snapshot. Then we need to play the edit log. It's like just playing some, I don't know if you're a musician, but for example, a MIDI file, right? When you store the keystrokes in a MIDI file, then you basically play through it. So you basically need to play the edit log to replay all the changes and apply them in here. And then you have restored everything. Then you need to wait for the reports of the data nodes to also get back the block locations. And then you have everything. The problem is that it takes half an hour and all your employees are basically blocked for half an hour. That is not good at all. So we didn't lose data. It could be worse. So we didn't lose data, but still we have this problem that it takes 30 minutes. Can we do better? The answer is yes, absolutely we can do better. One way to do that is to not let the edit log grow too big. At some point, you can just replay it and then recreate a completely new namespace file that will be bigger, of course, but then the edit log is back to 0, right? Then you have nothing now to replay. Then you again build an edit log. So regularly you do what is called the checkpoint. You recreate an entire snapshot of the namespace file. Okay, now there is an even better way of actually solving that issue. It's what is called the standby name node. The standby name node is just like the Vice President of the United States. Its only job is to be there in order to replace the president if the president is incapacitated. Right. Of course, there's yeah. Go ahead.
So we have a question. How often are the checkpoints?
Oh, it's up to you. I think that you can probably set thresholds. For example, if the size of the edit log grows too big, then if you cross a threshold, then it triggers a checkpoint. For example, that's what I can imagine. Or you can do it every couple of hours or every day, for example. And this is done by the standby name node, by the way, these checkpoints, right? All right. So the job of the standby name node is to be there to jump in immediately if the active name node is actually failing. And then there is not half an hour to wait because it's always ready at all times to jump in, right? So this is the idea. All right. And there is yet another improvement that is called the federated DFS. So this is basically the United States and this is Switzerland, right, with the contents. So the idea is that then you have several name nodes and every name node is responsible for part of the hierarchy, right? For example, directory foo is handled by that name node. Directory bar is handled by that name node. So this is a federated distributed file system, right? So this is how things work. And I hope that now you understand how, of course, it didn't happen overnight, right? This came year after year. So the developers of ATFS kept improving and improving and improving, and it got better with time. All right. Okay, still have a bit of time before the break. Yes, oh, almost. The break is actually coming soon. So I'm almost done with HDFS. I just wanted to say that the way you use it is actually on the command line, and it's very similar to the way you use your laptop to create files on the command line, create directories, and so on. Right. I think the bell is probably going to ring or has already rung. What if the standby name node also fails? Then yes, you have a problem then, absolutely. then I assume that maybe you can have more if you really want to take less risk. But in the worst case, what happens? You just wait for half an hour, right? So that's basically the idea. All right, that's the break. So I'll see you in 10 minutes. Then we'll finish that. There's only a few slides left, and then we'll move ahead to the textual data sets. See you in 10 minutes. Thank you.